Rotating black holes. So far, our treatment was for non-rotating, non-spinning black holes, Schwarzschild black holes. However, very likely all black holes rotate, just as planets and stars rotate. An isolated, uncharged rotating black hole, called a Kerr black hole, K-E-R-R, is completely specified by its mass and either its spin angular momentum or its rotation frequency. A rotating black hole's event horizon has a maximum rotation frequency such that the event horizon equator's tangential speed would be the speed of light. This rotation frequency is inversely proportional to its mass. For a 10 solar mass black hole, the maximum rotation frequency would be 1.6 kilohertz. The maximum rotation frequency for the supermassive black hole at the center of the Milky Way is 1 rotation every 4 minutes. If the Milky Way supermassive black hole were rotating at 1/10 of its maximum rotation frequency, then it would rotate once every 40 minutes. Plunging into the rotating black hole has more possibilities and is more interesting than plunging into the non-rotating black hole, as we will see. Rotating black holes are very complicated, but we will look at some key features. A non-rotating black hole has one mathematical surface, the spherical event horizon at the Schwarzschild radius, out of which neither matter nor light can escape and inside which no shell observers are possible, and one central singularity point into which all matter and light inside the event horizon inescapably plunge. In place of a singularity point, a rotating black hole has a singularity ring, the red ring in this image, in the equatorial plane perpendicular to its rotation axis. This is the rotation axis and the direction of rotation. Instead of one spherical event horizon, a rotating black hole has 4 interesting surfaces nested within one another. The non-rotating event horizon is replaced by 2 outer nested surfaces, which we will cover first. 2 inner nested surfaces are associated with the singularity ring, which we will cover later after covering orbits and time dilation. 3 of the surfaces are shown in this image, which represents a moderately rotating black hole. We see the pink, yellow, and blue surfaces. The shapes of the surfaces are more complicated for a black hole rotating near its maximum possible rate, as we will see later. Here is a different, simplified, and exaggerated representation for a moderately rotating black hole. This is the spin axis and the z-axis, and it's rotating about the z-axis. This is a vertical cross-section in the y-z plane, except that the singularity ring, this black dotted ring, is being shown in the x-y plane. So, diagram's a little complicated. In this diagram, the radii of the 4 surfaces are the distances to the singularity ring, not to the origin. I'm not sure these shapes are quite right, but these details won't be important to us. The outermost and innermost surfaces are also a function of the polar angle from the rotation axis. The singularity ring here is in the xy plane, centered on the origin, which is here. The ring radius is proportional to the black hole's spin angular momentum divided by its mass, and it has a maximum value of half the Schwarzschild radius. If the Milky Way supermassive black hole is rotating at 10% of maximum, the ring radius would be 1/20th of its Schwarzschild radius, about 90% of the sun's radius, I think. Now we should think of this singularity ring as being infinitesimally thin. It's not a donut or a torus, it's an extremely thin ring in the xy plane. The solid red line oblate spheroid in this image is the outer event horizon. Any matter or light that crosses into the outer event horizon cannot escape and return to our universe. More on this later. The outer event horizon for a rotating black hole is closer to the singularity ring than the Schwarzschild radius for a non-rotating black hole. At maximum rotation, its distance to the singularity ring is half the non-rotating distance, half the Schwarzschild radius. This will be important for orbits and time dilation. The outer solid yellow line surface, shown here as an oblate spheroid, is the outer ergo surface, which is near to the non-rotating black hole Schwarzschild spherical event horizon in the equatorial plane and touches the outer event horizon on the axis of rotation. I might sometimes misspeak and say ergosphere when I mean to say ergo surface, but hopefully I won't. Matter anywhere inside the outer ergo surface cannot be at rest relative to a faraway observer. Matter must be moving radially, tangentially, or both. But plunging into the singularity ring is not the only possibility here, as we will see later. The outer ergo surface is also called the static limit. Inside it, no rocket can maintain a stationary position, and no shell observers are possible. Outside the outer ergo surface, it is at least theoretically possible to maintain a stationary position, and shell observers are possible, but not inside the outer ergo surface. So for a non-rotating black hole, we had one surface, the event horizon, and inside it there could be no shell observers, and matter and radiation would plunge into the singularity. For the rotating black hole, we get two surfaces. The red surface here, inside which matter and light plunge in, cannot escape to our universe, and the yellow line surface here, inside of which there can be no shell observers. The region between the outer ergo surface and the outer event horizon, shown here in blue, is called the ergo region or the ergosphere, even though it is not a sphere. Within the ergo region, a plunging, freely falling observer takes an inward spiraling trajectory, not radial, but an orbiting observer can orbit at constant distance from the singularity ring. A free fall plunging observer who plunges into the singularity ring will do so in a slightly shorter wristwatch time for a rotating black hole than for a non-rotating black hole. Circular orbits of a rotating black hole. In this diagram, the horizontal axis is distance from the singularity ring at the left. Singularity ring is here. This is distance in Schwarzschild radii. As the rotation of the black hole goes from 0 to maximum, the outer event horizon moves closer to the singularity ring. From 1 Schwarzschild radii radius for a non-rotating black hole to 1/2 Schwarzschild radius for a maximally rotating black hole. So this red arrow. The ring of fire, or photon sphere, for a non-rotating black hole. For a non-rotating black hole, it's at 1.5 Schwarzschild radii, becomes a shell of fire for a rotating black hole. A fixed number of complex three-dimensional light orbits between two equatorial orbits. An inner prograde light orbit, prograde means in the same direction as the black hole rotation. An inner prograde light orbit that pushes in close to the outer event horizon. And an outer retrograde light orbit that pushes out toward 2 Schwarzschild radii. So these are the green arrows. Mostly we will consider circular orbits in the equatorial plane of the singularity ring, orbiting in the same direction as the black hole rotation. In the equatorial plane, the innermost stable circular orbit, the ISCO, for a non-rotating black hole. For a rotating black hole, the ISCO is at 3 Schwarzschild radii. For a rotating black hole, we get 2 ISCOs. One for motion in the same direction as the black hole rotation, prograde, which is this blue arrow, and one in the opposite direction, retrograde. Stable circular orbits in the same direction as the black hole's rotation, prograde, outside the outer event horizon, can reach closer distance to the outer event horizon and to the singularity ring than do stable circular orbits for a non-rotating black hole, down to 1/2 the Schwarzschild radius for a maximally rotating black hole. Within the shell of fire, inside the outer ergo surface, and close to the outer event horizon. The retrograde ISCO gets pushed toward 4.5 Schwarzschild radii. The closer in, stable, prograde circular orbits lead to increased temperature of and radiation from an accretion disk, which we will cover, that circles around the rotating black hole. In this graph, the horizontal axis is the amount of rotation, with 0 at the left and the maximum possible value at the right. The blue curve is the radius of the prograde ISCO in Schwarzschild radii. It's 3 on the left and 1/2 on the right, maximum rotation. It doesn't change very rapidly as we go from no rotation to 10% to 20%. Time dilation. We also have higher time dilation and gravitational redshift for the prograde ISCO than for a non-rotating black hole. This is the red curve. The maximum time dilation for a non-rotating black hole ISCO is 1.4. The time dilation increases with spin and approaches infinity as the rotation approaches its theoretical limit. So as we increase the spin, the ISCO pulls in closer and the time dilation at the ISCO increases. However, physicists believe that rotating black holes might not be able to exceed 99.8% of the theoretical limit for rotation. At that rotation, the maximum time dilation for a stable circular orbit is 10.8. For every year a spaceship spends orbiting at this prograde ISCO, faraway observers in the universe age 10.8 years. In the television series Andromeda from 2000, in the pilot, the starship and captain drift extremely close to a black hole and experience a time dilation factor of 1,000,000. They don't age at all while the universe ages 300 years. So that is unrealistic for a stable circular orbit. Perhaps it could be one pass of an extremely close-in elliptical orbit, but probably not. In the movie Interstellar, for the storyline between the astronaut and his daughter back on Earth, the director needed a time dilation for the close-in, stably orbiting Miller's planet of 7 years per hour, or 61,400. To get this huge time dilation, physicist Kip Thorne imagined the 100 million solar mass supermassive black hole as having a huge rotation within 1 part in 100 trillion of the theoretical limit for black hole rotation. However, physicists, including Kip Thorne, believe that rotating black holes might not be able to exceed 99.8% of the theoretical limit for rotation. At that rotation, the maximum time dilation for a stable circular orbit is 10.8. So the extreme time dilation for Miller's planet is theoretically possible, but might not be possible or anywhere close to possible. Interstellar ignored gravitational redshift of their communication signals, which would have been 61,400 from Miller's planet. This is a plot hole in the movie, and the astronauts could have been able to tell what the time dilation was down on Miller's planet without going there. Interstellar mostly ignored the huge energy changes required to change orbit so close to a black hole. It is supposed that getting down to Miller's planet required gravitational slingshots around a convenient neutron star and then a convenient intermediate mass black hole near Miller's planet, all in orbit around Gargantua, exactly where they're needed in order to do the slingshot. And that they would again be where they were needed when the astronauts wanted to return. Okay, sure, why not? It's science fiction. I posted a supplementary video covering effective potential energy for non-rotating black hole orbits, but adding rotation increases complexity, and we won't cover those potential energies. Higher time dilations and gravitational redshifts can be achieved for unstable circular orbits close to the outer event horizon. This is a science fiction possibility for using a powered spaceship to intentionally hide out from the present universe and skip ahead to the future for a hypothetical advanced civilization, space traveler, who can stand the tidal acceleration and has an unrealistic capability to boost the energy of their spacecraft to a multiple of its rest mass energy. But this is unlikely. Frame dragging and the shell of fire. The rotating black hole drags spacetime in its rotation direction. This is called frame dragging. This is strong near the event horizon and falls rapidly with distance. A plunging observer plunging radially in free fall relative to local space would be seen by shell observers to be pulled circumferentially along with the frame dragging and black hole rotation. Imagine a leaf floating on top of a water vortex, heading down a drain, circularly vortexing in. To a faraway observer, the orbiting object's angular momentum and energy are neither constant nor conserved for orbits around the rotating black hole. An orbit that starts in a plane that is not equatorial will not remain in the plane. The object will move in a complex trajectory in 3 dimensions, such as the following: side view and top view. The shell of fire light orbits that are not equatorial look something like this. Later we will see that visual effects for an observer near a rotating black hole are even wilder than those near the non-rotating black hole. In the equatorial plane outside the outer ergo surface, a shell observer's weight will be radial, but if the observer drops a ball, it will not fall perfectly radially, but will deviate spinward due to frame dragging, I think. The Earth's rotation causes frame dragging of spacetime, but it is so small, less than a trillionth of Earth's rotational speed, I believe, that it has been detected but not verified to good precision. Penrose processes. If a black hole rotates at least 94.3% of maximum, the prograde ISCO pulls inside the outer ergo surface. In that case, there are theoretical processes called Penrose processes, whereby an advanced civilization could send a probe through the outer ergo surface in a retrograde orbit into the ergo region not cross the outer event horizon, extract spin angular momentum and energy from the rotating black hole's frame dragging, slightly slowing the black hole rotation, expel some of its mass into the outer event horizon, and exit the outer ergo surface, where the advanced civilization could capture the probe and harvest the energy extracted from the rotating black hole. In this case, the rotating black hole loses a little spin angular momentum and rotational energy. I don't understand the details, but the rotating black hole is an immense energy source waiting to be tapped by an advanced civilization. An advanced civilization might also be able to harvest the quasar radiation from an accretion disk. Black hole interior. We have finished discussing the outer event horizon and phenomena outside it, except for accretion disks, which we will cover. Now we will cover the interior of the rotating black hole. Within the outer event horizon, which is here, not touching it, the dashed yellow line ellipsoid is the inner event horizon or inner Cauchy horizon, which surrounds the singularity ring but does not touch it. Within the inner event horizon, touching it only on the rotation axis, the dashed red line ellipsoid is the inner ergo surface, which touches the entire singularity ring. Stable orbits exist only outside the outer event horizon, the solid red line surface in this diagram. But an observer can also remain in orbit at constant radius r inside the inner event horizon, including close to the singularity ring, though these orbits must be in the same direction as the black hole's rotation, prograde, and those orbits will be unstable. Between the outer event horizon and the inner event horizon, it is not possible to remain in orbit at constant radius. An observer who plunges from the ergo region through the outer event horizon will continue to plunge and will cross the inner event horizon. The observer may plunge and ram into the singularity ring, the end, but that's not the only possibility. Theoretically, it is possible, it might be possible, to use a curving free fall transfer orbit to go from a stable or unstable prograde orbit outside the outer event horizon. So here, this is showing the ISCO. So this is a curving free fall transfer orbit. And then a course correction is made, and we end up in a unstable circular orbit inside the inner event horizon, inside the Cauchy horizon. So we might be able to end up in an unstable orbit extremely close to the singularity ring. This diagram is looking down the rotation axis, down the z-axis, at the equatorial xy plane for a black hole rotating at 87% of maximum. Of course, once this probe crosses the outer event horizon, here, it can no longer communicate with our universe. Now, switching back to the YZ plane, we'll simplify that the transfer orbit as just this red line, because we're going to ignore the angle in the XY plane. So we were at some orbit here, and we transferred a curving transfer orbit, and we got ourselves inside the inner event horizon, and we got ourselves into an unstable circular orbit inside the inner event horizon. Physicists say that it is theoretically, mathematically possible to plunge through the center of the singularity ring to pass into another universe, not our universe, but where Einstein's general relativity still applies. I'm showing this possibility as the red, then blue paths. You would escape out the event horizon of the alternate universe black hole, as the book I read calls it, though white hole may be the emerging name for it. There would be no possibility of returning to or communicating with our universe through the original black hole. Oh, perhaps there could also be a different black hole-white hole pair from that universe to our universe. Another way to pass through the center of the singularity ring would be to plunge along the rotation axis of the supermassive black hole, shown in green here. Both the blue and green paths require certain rocket thrusts inside the inner Cauchy event horizon that might be impractical. This sounds like science fiction. It might be that this is later proven to be impossible, or perhaps only possible for radiation or individual elementary particles. I have not calculated the tidal acceleration along this path. It might be fatal. This is not a wormhole, which we discuss later. So, the singularity of a rotating black hole is a ring through which a spaceship might pass undamaged into a different universe if it could survive the tidal forces, but maybe this is not possible. The rotating black hole may provide a one-way gateway to other universes, but maybe only for radiation, or maybe it's not possible. There is a region inside the event horizon in which a spaceship in a range of energies does not inevitably move toward the singularity ring, but can be repelled away from it, and might be able to escape our universe. Black hole shadow. Here is a GIF of a vertical cross-section of how the four black hole surfaces, shown in white, and the black hole shadow change with the black hole's rotation, from zero rotation to maximum, viewed along the equatorial plane. Some shapes and sizes here differ from other representations, which I don't understand but won't concern us. Let me pause the video at 0 rotation. And let me draw the axis of rotation. This is the axis of rotation. It's rotating in this direction. At 0 rotation, we're looking at a non-rotating black hole. So this is the non-rotating black hole Schwarzschild event horizon at the Schwarzschild radius. The ISCO is located at 3 Schwarzschild radius, so it's about here. The ring of fire is located at 1.5 Schwarzschild radii, so the ring of fire is maybe here. Inside the ring of fire, light spirals into the event horizon. Now the reds, I'm not going to draw the entire thing, but the red circle here, going all the way to here, at 2.6 Schwarzschild radii, that is the perceived location of the ring of fire, as perceived by an outside observer, taking into account the light trajectories curved by the strong spacetime curvature. Within the perceived ring of fire is the black hole shadow, the black area. An observer in the equatorial plane sees no background stars straight through this region due to the strong curvature of spacetime in this region, altering light trajectories. We will see later that these star positions will move to points outside the ring of fire. Light inside the ring of fire is spiraling into the outer event horizon, so we don't see it. Now, first let's add 10% of rotation, so comparable to the Milky Way supermassive black hole's probable rotation. This, I couldn't stop fast enough. This is 20% rotation. And the event horizon is nearly unchanged. The black hole shadow and ring of fire have moved slightly to the right. Now let's add about 90% of rotation. Okay, this is about 90%. The black hole shadow has moved laterally from our perspective. It has changed shape. It is scrunched to the left and bulging out to the right. The singularity point has become a ring. Here to here. We're only looking at the YZ plane, So we only see 2 points of the ring because the ring is in the XY plane. The singularity point has pushed out to become a singularity ring. The inner event horizon, this ellipse, pushes out from the singularity ring. The outer event horizon, this surface, pulls in toward the inner event horizon and the singularity ring. At high rotation, the outer event horizon and the inner event horizon move close to one another. And the inner ergo surface takes this shape. Let's go to maximum rotation. So at maximum rotation, the inner and outer event horizons are very close to one another. Now, the prograde ISCO has moved from here close in here. So it's very close to the inner event horizon, the outer event horizon, and it's pretty close to the singularity ring. And there is strong time dilation and gravitational redshift in this case. This completes most aspects of rotating black holes. Now we're going to cover part 2 of accretion disks, jets, and quasars. Black holes look black, right? When does a black hole not look black? A black hole may have a hot, light-emitting accretion disk of dust, hot gas, and very hot plasma in orbits outside the event horizon. The material could be pulled tidally from a binary companion star, as shown in this artist's conception of a stellar mass black hole accretion disk. Or a star coming too close can be shredded or eaten by the black hole. A large accretion disk can be a light year in diameter. For a non-rotating black hole, the siphoned material remains in the plane of the orbit of the binary companion star, as angular momentum is conserved. Tidal acceleration from the black hole mass compresses the accretion disk so that it is thinner closer to the black hole. Collisions, friction, and electromagnetic interaction between particles cause the material to heat up and radiate electromagnetic radiation as it loses energy and cascades inward through a sequence of stable orbits, stable prograde orbits if the black hole is rotating, then spirals into the event horizon. For a rotating black hole, the accretion disk might be complicated if the plane of the outer accretion disk is different than the rotating black hole's equatorial plane. Frame dragging will alter the particle trajectories increasingly as they cascade closer inward. Astronomers have no visible light images of any black hole accretion disks. You will see artist representations, but details may not be correct, especially colors. The inner portion of the accretion disk heats up to probably billions of Kelvin, ionizes into a plasma, generates its own strong magnetic fields independent of any electrical charge on the black hole, and emits X-rays most intensely. Less intensely but still bright will be gamma rays and ultraviolet, and less intensely visible light and infrared light, all of which propagate to the universe and we can potentially detect. Visible light would probably look painfully bright blue-white. As for this O-type star, not an accretion disk. Astronomers see the bright visible light and radio emission from distant quasars, called active galactic nuclei, AGNs, believed to be the accretion of multiple solar masses per year onto rotating supermassive black holes at the centers of young galaxies far away and long ago. However, no astronomical images of distant quasars have enough resolution to show the accretion disk or the black hole shadow of a distant quasar. This image is an artist's interpretation. Hot, dense, infalling plasma that has reached near the event horizon, which would be in here and we don't even see it, can also electromagnetically eject itself outward as two high-speed relativistic jets, perpendicular to the accretion disk, typically along the rotation axis of the rotating black hole, especially for supermassive black hole quasars. So this is one jet. The other jet would be opposite it, but it's not being shown here as it's behind this accretion disk and they didn't want to complicate the image. These jets emit light and radio waves, and they are still luminous thousands of light years from the black hole. Some of the ultra-high energy cosmic rays detected on Earth may have originated in the jets of supermassive black holes of other galaxies. When the jet is pointing toward us, relativistic beaming greatly increases the observed brightness, and astronomers call such objects blazars. These jets can act as a wind that pushes galactic gas and dust away from the rotation axis of the black hole and reduces star formation in that region, or it can compress and heat the gas and dust and increase star formation in that region. For a non-rotating black hole, again, this horizontal axis is amount of rotation, maximum, minimum, 0. For a non-rotating black hole, accretion disk particles, they can radiate up to 5.7% of their rest mass energy before plunging into the event horizon. That's 8 times the energy that nuclear fusion releases. X-rays would be radiated most intensely, but also all other electromagnetic wavelengths. For a rotating black hole, the ISCO for a particle orbiting in the direction of the black hole's rotation pulls in closer to the event horizon, and singularity ring. The particle orbiting at the prograde ISCO has a lower potential energy relative to a non-rotating black hole. For a black hole rotating at half the maximum rate, which is here, the accretion disk particles can radiate up to 8.2% of their rest mass energy. For a maximally rotating black hole, accretion disk particles can radiate up to 42% of their rest mass energy, 60 times the energy that nuclear fusion releases. Extremely bright in X-rays, gamma rays, and optically. That's where the energy for quasars is coming from. Here is a different artist's conception showing the accretion disk and jet. Jet particles are going outward. They might be spiraling outward. Accretion disk particles are slowly moving inward, and the jet is relativistically moving outward. Some aspects of this representation seem doubtful to me, as we will discuss, but I'm presenting it because it shows the tip of the relativistic jet nicely. The jet is not emitted by the event horizon. Some fraction of the plasma particles that get in close to the event horizon, they spiral from the inner accretion disk to the jet and then spiral outward forever at relativistic speed. But I don't know the plasma physics and trajectories between the inner accretion disk and the tip of the jet. This accretion disk is represented as a much lower temperature than I think a real accretion disk would be. I think most of this disk would be bright blue-white, or at least the inner portion. However, the artist wanted to show the hot tip of the jet, not blinded by the bright disk. For this image, the disk is rotating left to right in the foreground. Of course, the tangential velocity increases closer in, and it's half the speed of light at the ISCO of a non-rotating black hole. Due to relativistic Doppler shift, the light is shown brighter and bluer whiter coming toward us here on the left side, and dimmer redder moving away from us on the right side. However, I don't think we would see a color difference if the accretion disk is very hot. This representation shows the disk as dim and brown close to the black hole shadow. This is brown and this is brown. I believe the artist is representing the gravitational redshift close to the black hole. However, if the accretion disk is very hot, I think we would see bright blue-white down to the ISCO. Visible light would be redshifted to infrared, but ultraviolet would be redshifted to visible. These artist representations do not properly represent the bending of light near the black hole. The accretion disk would not look like a planar disk to an observer. I'll show more accurate simulations of the accretion disk later in the course, after we learn how the trajectories of light rays bend. This is an actual image from 2019 of the accretion disk around the 6 billion solar mass supermassive black hole M87 star at the center of the supergiant elliptical galaxy M87, 53 million light-years from us. Most other images of an accretion disk or black hole are artist's conception. This false color image was taken in polarized radio waves, not visible light, with the Event Horizon Telescope, which is a radio telescope, using very long baseline interferometry, VLBI, which has the required small angular resolution. Radio waves pass through dust that would block visible light. The temperature of this accretion disk is around 20 billion Kelvin. So it is emitting gamma rays and X-rays more strongly than visible light, more strongly than radio waves, though this image is in radio waves. This supermassive black hole is rotating at 90% of the theoretical rotation limit. Accretion disk particles turn about 15% of their rest mass energy into gamma rays and X-rays before spiraling into the event horizon. The bright light at the bottom of this image is presumably due to the Doppler shift of the accretion disk traveling toward us and away from us dimmer at the top of the image. This accretion disk is believed to be nearly edge-on to us, yet appears face-on to almost all observers due to the gravitational bending of light trajectories. The blurring of this image is due to the effect of gas between us and M87 star. Here is a much wider image of the core of M87 in visible light, showing one long jet to the right. In 2022, astronomers produced a good radio image of the Sagittarius A star supermassive black hole at the center of the Milky Way. The Milky Way supermassive black hole has a low mass accretion disk totaling about the mass of Jupiter that extends about 1,000 astronomical units, 1/100th of a light year. Our supermassive black hole is not presently a powerful quasar. Some of the stars with close approaches to the supermassive black hole plow through the accretion disk. If a star the mass and size of the Sun came within 10 astronomical units of the supermassive black hole, about Saturn's orbit around the Sun, the supermassive black hole would siphon mass from the star's outer layer to the accretion disk. For more information, you can read about Roche lobe and Roche lobe overflow, for example, on Wikipedia. One of the stars that orbits the supermassive black hole does come within 13 astronomical units of the supermassive black hole every 12 years, plowing through the accretion disk, but I don't know its mass or size or whether it is losing mass to the accretion disk. Though the Milky Way supermassive black hole does not seem to have strong jets currently, the core of the Milky Way galaxy has produced huge gamma ray and X-ray Fermi bubbles, the size of the galaxy, out of the plane of the galaxy, as shown in this artist's conception. The blue is X-ray emissions, purple is gamma ray emissions, and is the Fermi bubble. The Fermi bubbles may have been produced during a period of 100,000 years, beginning about 2.6 million years ago, when the supermassive black hole consumed materials of about 1,000 to 10,000 solar masses and had jets. Black holes with accretion disk plasmas may also emit X-ray flares. This image is a simulation of a flare caused by very energetic magnetic reconnection of magnetic field lines in the plasma. Magnetic reconnection is also thought to be the heat source that heats the sun's corona outside the photosphere to millions of degrees, millions of Kelvin. Accretion disks and jets are one way for astronomers to find black holes. Black holes that are binaries with stars are detected by the cyclical Doppler shift of the star in its orbit. Also, gravitational waves can identify a merger of two compact objects into a stellar mass black hole. Certainly, there could be isolated black holes without accretion disks or jets that astronomers cannot detect, perhaps many millions of them in the galaxy.